Testing, testing. All right. Good afternoon, everybody. So, today, what we're going to be looking at is some more notes on binary and practicing with binary, kind of getting a little bit of a more of an understanding about what binary is and what it's used for. First off, though, we want to kind of recap what our project is and just kind of remind ourselves of what our goal is. What are we trying to do? So, next class, I'll have you guys pick out groups. 3 people is ideal, but we can make it work with 2 and we can make it work with 4. But 3 is ideal. So one person is going to be given the message to send, and then they are going to have to encode and send that signal to person number 2. Person number 2 is going to convert that signal into another type of signal. And then person number 3 is going to receive that final signal and decode it. Now, remember that you have to send the signal all the way down the hallway. So the first leg of that trip is 150 feet. The second leg is around a corner. So the person 2 and person 3 cannot be able to see each other. They cannot see each other. And they only have to be 10 feet apart. So if we try to think about like what is the benefit of using different types of waves, you probably could get an idea for the benefits, the pros and cons of each one. So what's really good about light as opposed to sound? Well, light travels very far and very quickly, and it's very easy to kind of see something really far away, but it's hard to hear something really far away. So the first leg of our journey, where we have to do a very long leg, it makes sense to use something like light, because one person could be at one end of the hallway and you can see them. You might not be able to hear them, especially if there's a lot of things going on in the hallway. So sound over that distance, not as good. But light works really well for that. What sound is really good at is being able to bounce around a corner. So in the second part of the signal sending, when you're sending signal 2, that second leg of the journey, it has to go around a corner. Now, light doesn't go around corners very well, but sound does. And because that's a short, only 10 feet, it doesn't matter that sound doesn't travel very far distances, because you don't need it to go very far. So that's the benefit of kind of looking at it in terms of that. The next thing that we want to look at is AM and FM, and we'll talk more about this later on. Amplitude modulated, if we're talking about light, would be bright light or dim light. If we're talking about sound, it would be loud or quiet. So there's some benefits and some cons about that one, right? Might not be able to shine a light, varying levels of brightness. You might not. Sound, it might be hard to tell what's a loud sound versus a quiet sound versus somewhere in the middle. FM modulated for light would be different frequencies of light, so different colors of light, red and blue. For sound, it would be different frequencies of sound, so high pitch and low pitch. Again, some of the pros and cons, again, depending on what you're doing, might be hard to switch the color of your light. For the sound, it might be hard to switch the pitch of your sound, or the person receiving those sounds might be tone deaf, might not be able to tell what's a higher pitch or a lower pitch or whatnot. So these are all things that you guys are going to have to figure out in your groups and work around and solve.
Yeah, I can hear you. I'll be right there. You know all this talk about.
hold on, let me get the captions fixed here real quick. Oh, actually, I'm not going to do captions at all. I'll let YouTube caption it out for us.
About next generation networks and who has the best reception. Can you hear me now? Truth is, no one would be able to hear anything if it weren't for the teamwork of James West and Gerard Sessler. Between 1962 and 64, at Bell Laboratories, James E. West, American, and Gerard Sessler, German, developed the electroacoustic transducer electret microphone, which we now call the electret condenser microphone. Before this invention, condenser microphones needed a battery or an external power source to power the electromagnetic field needed to convert sound into an electrical signal. West and Sessler introduced the electret into the equation. This electret harnessed the electromagnetic field of enough contained electrons to produce the charge needed for the microphone's capacitor. Not only are electret condenser microphones lightweight, but they're relatively affordable to produce, and they capture the human voice perfectly. Since 2007, an estimated 2 billion electret microphones have been produced each year. They're in cell phones, laptops, tablets, hearing aids. I couldn't find a hearing aid, so this is you pretending that there's a hearing aid right there. Yeah, good. That's perfect. If you've ever said the words Siri, Alexa, or OK Google and expected a machine to respond, you're talking to a microphone designed by James West and Gerard Sessler. Imagine 2 people from different countries with different shades of skin working together to better the future. That was James West and Gerard Sessler. This is Balance.
All right, so that was just a little bit of a history on microphones and kind of how they work. A real quick overview of how they work. So again, remember that we need certain team members, right? We need different people that are responsible for different parts. However, doesn't mean that that person is the only person that's going to be doing that part of the assignment, right? You all need to do all of the assignments so that you have an understanding about all the parts. It's just on the actual test day, those are the people that are going to do those specific roles. We need sending technician, right? This is the person sending that signal. We need receiving technician, a person receiving the signal. Now, in truth, we're going to need multiple of these things. If you have 3 people, right, the first person is going to have to take the word that's given to them, convert it into binary, send out that binary through light. The second person is going to receive that light signal and convert it to sound. And they can directly do that. They don't need to figure out what the word was. They just pass along the message that's sent to them. The third person is going to receive that sound, get that binary from the sound, and turn it back into a word. Now, 3 is perfect. If you have 4 people for this, again, we can set something up where the 4th person can either be helping that first person encode the information initially and get that binary signal, or they can be working with the last person decoding that message, taking that binary and figuring out what the message was supposed to be. Again, just a reminder about how we can encode information on waves. If we're sending them signal 0011, 01, 00010, right? That's what we're trying to get across. We could send it in electronic digital signal with basically ons and offs. We could do an AM signal, amplitude modulated, so flat for zeros and then spikes for ones. We could do an FM digital signal, right? This would be where it's low frequency and then high frequency, and then low frequency and then high frequency. Again, remembering that different frequencies for visible light are different colors. So opposite ends of the spectrum, we've got things like red and blue are different frequencies. So a frequency modulated light that's in the visible range would change color. Again, kind of recapping how the telecommunications stuff works. We're going to kind of watch this video that explains it.
My name is Tess Winlock. I'm a software engineer at Google. Here's a question. How does a picture, text message, or email get sent from one place to another? It isn't magic. It's the internet, a tangible physical system that was made to move information. The internet is a lot like the Postal Service, but the physical stuff that gets sent is a little bit different. Instead of like boxes and envelopes, the internet ships binary information. Information is made of bits. A bit can be described as any pair of opposites, on or off, yes or no. We typically use a 1 meaning on or a 0 meaning off. Because a bit has two possible states, we call it binary code. 8 bits strung together makes 1 byte. 1,000 bytes all together is a kilobyte. 1,000 kilobytes is a megabyte. A song is typically encoded using about 3 to 4 megabytes. It doesn't matter if it's a picture, a video, or a song, everything on the internet is represented and sent around as bits. These are the atoms of information, but it's not like we're physically sending ones and zeros from one place to another, one person to another. So what is the physical stuff that actually gets sent over the wires in the airwaves? Well, let's look at a small example here of how humans can physically communicate to send a single bit of information from one place to another. So say that we could turn on a light for a 1 or off for a 0, or use beeps or similar sort of things of like Morse code. These methods work, but they're really slow, error-prone, and totally dependent upon humans. What we really need is a machine. So throughout history, we've built many systems that can actually send this binary information through different types of physical mediums. Today, we physically send bits by electricity, light, and radio waves. To send a bit via electricity, imagine that you have 2 light bulbs connected by a copper wire. If one device operator turns on the electricity, then the light bulb lights up. No electricity, no light. If the operators on both ends agree that light on means 1 and light off means 0, then we have a system for sending bits of information from one person to another using electricity. But we have a problem. Let's say that we want to send 5 zeros in a row. Well, how can you do that in such a way that either person can actually count the number of zeros? Well, the solution is to introduce a clock or a timer. The operators can agree that the sender will send 1 bit per second, and the receiver will sit down and record every single second and see what's on the line. To send 5 zeros in a row, you just turn off the light. Wait 5 seconds. The person on the other end of the line will write down all 5 seconds, say 0, 0, 0, and for ones, do the opposite. Turn on the light. Obviously, we'd like to send things a little bit faster than 1 bit per second, so we need to increase our bandwidth, the maximum transmission capacity of a device. Bandwidth is measured by bit rate, which is the number of bits that we can actually send over a given period of time, usually measured in seconds. A different measure of speed is the latency, or the amount of time it takes for 1 bit to travel from one place to another, from the source to the requesting device. In our human analogy, 1 bit per second was pretty fast, but kind of hard for a human to keep up with. So let's say that you want to actually download a 3 megabyte song in like 3 seconds. At 8 million bits per megabyte, that means a bit rate of about 8 million bits per second. Obviously, humans can't send or receive 8 million bits per second, but a machine can do that just fine. But now there's also a question of what sort of cable to send these messages over and how far the signals can go. With an Ethernet wire, the kind that you find in your home or office or school, you see really measurable signal loss over just a few hundred feet. So if we really want this internet thing to work over the entire world, we need a different way of sending this information really long distances. I mean, like across an ocean. So what else can we use? Well, what do we know that moves a lot faster than just like electricity through a wire? Well, light. We can actually send bits as light beams from one place to another using a fiber optic cable. A fiber optic cable is a thread of glass engineered to reflect light. When you send a beam of light down the cable, light bounces up and down the length of the cable until it is received on the other end. Depending on the bounce angle, we can actually send multiple bits simultaneously, all of them traveling at the speed of light. So fiber is really, really fast. But more importantly, the signal doesn't really degrade over long distances. This is how you can go hundreds of miles without signal loss. This is why we use fiber optic cables across the ocean floors to connect one continent to another. In 2008, there was a cable that was actually cut near Alexandria, Egypt, which really interrupted the internet for most of the Middle East and India. So we take this internet thing for granted, but it's really a pretty fragile physical system. And fiber is awesome, but it's also really expensive and hard to work with. For most purposes, you're going to find copper cable. But how do we move things without wires? How do we send things wirelessly? Wireless bit sending machines typically use a radio signal to send bits from one place to another. The machines have to actually translate the ones and zeros into radio waves of different frequencies. The receiving machines reverse the process and convert it back into binary on your computer. So wireless has made our internet mobile, but a radio signal doesn't travel all that far before it completely gets garbled. This is why you can't really pick up a Los Angeles radio station in Chicago. As great as wireless is, today it still relies on the wired internet. If you're in a coffee shop using Wi-Fi, then the bits get sent through this wireless router and then are transferred to the physical wire to travel the really long distances of the internet. The physical method for sending bits may change in the future, whether it's lasers sent between satellites or radio waves from balloons or drones, but the underlying binary representation of information and the protocols for sending that information and receiving that information have pretty much stayed the same. Everything on the internet, whether it's words, emails, images, cat videos, puppy videos, all come down to these ones and zeros being delivered by electronic pulses, light beams, radio waves, and, lots and lots of love.
All right, so there was one thing in there that we do want to kind of make sure is really, really obvious, and that was when communicating between two people, that's something you're going to have to do. And it was the sending multiple of the same thing. How do you send multiple zeros in a row? How do you send multiple ones in a row? And that was a key thing that you guys are going to need to kind of figure out.
5 zeros in a row. Well, how can you do that in such a way that either person can actually count the number of zeros? Well, the solution is to introduce a clock or a timer.
So their solution, obviously the one that we use in real life, is using a clock or timer to know when we're supposed to be measuring the next signal. In practice, this is going to be very, very hard for groups. So you don't need to, you can, if you want to, do it using a timer-based system. Another way is to introduce a third option into our binary system. So really it's sort of trinary in terms of high pitch, low pitch, and no pitch, right? So in between the high pitch signals, you would just have a blank. And we'll kind of talk more about what that is here in a second. Similarly with the light, right? You'd be able to show one light, show another light, and then have nothing in between. And so we'll kind of work our way around that system, but definitely something that you need to keep an eye on because it will come up. You guys are going to be brainstorming, figuring out how you guys can do this, how you guys can send signals with light, send signals with sound, because that's going to be your goal for this project. We'll have a lot more time to think about and work on that next time. Again, just wanted to reintroduce this or remind you guys of this. For sound, amplitude modulated would be, again, amplitude is volume for sound, so it would be a loud or quiet sound. Amplitude modulated light would be a bright light or a dim light. For frequency modulated, frequency in sound is pitch. So frequency modulated sound would be a high pitch or a low pitch. For light, frequency is color. So it'd be a different color. So like red versus blue type of thing. So again, you guys are going to have to decide how you guys want to be transmitting. Do you want to use amplitude modulation? Do you want to use frequency modulation? And it may be the same and it may be different. That's totally okay. It may depend on your group. You will need to use both sound and light. So again, just something to kind of keep in mind. We're going to give you some examples of how you could possibly do this if you had cell phones or tablets or Chromebooks to send some of these signals. Here are some options, right? So we could flip between some slides. I would recommend kind of having a blank slide in between so that you have that reset so that you know like 1-1 is not just me hovering at the page for too long type of thing. So again, figuring out a way to send it so that you can know what those are. Same thing, you could do same thing with speakers, right, around the corner. So we've got our 440, and then we've got another frequency here. Right, so our low frequency, our high frequency, would somebody be able to hear those and tell them apart? Would somebody be able to write down what those are? Hopefully. There is an online piano that you guys can do. One issue that people have had in the past is you're picking a low note, you're picking a high note. Sometimes people will accidentally press a different note, and that can throw off your whole test if somebody accidentally presses something else. So you gotta think about some of those things. I like this way so that you can kind of have them both on the same page at the same time. So there's my 0. There's another 0, 2 zeros in a row. Maybe I need a 1 next. Maybe I need 3 1s in a row. Right? So lots of different ways that you guys could organize and set something up. I like this more than the piano, again, because I'm not worried about accidentally pressing one in between. Again, you just have to be kind of careful with how you choose to do things.
It's a common theme throughout the modern world that everything in a computer's brain comes down to ones and zeros. You've most likely heard that this code of ones and zeros is what's referred to as binary. And while almost everybody knows that this is somehow related to what computers do, very few of us seem to understand what binary is or why computers use it. If you want to know, then this video is for you, because it's actually a very simple concept and still quite fascinating. Before we get to computers, let's talk about what binary itself is, as it existed long before computers did. Binary is nothing more than a system of counting. To understand how it works, let's look at 2 other systems of counting, tally marks and the glorious base 10 positional that we all know and love today. Tally marks are the simplest counting system imaginable. However many things you have, you put down that many marks, easy as pie, but not very efficient. Meanwhile, base 10 positional, which is what we use today, uses a different symbol to represent different amounts of things. With the numbers 0 through 9, we can recognize that each symbol indicates a different amount of things. If we need to represent something higher than 9, we add a digit to the left, roll its first digit back to 0, and start over. This system is very efficient compared to tally marks because each digit we add exponentially increases the amount of things we can represent. Because in this system we add a new digit every 10 things, each digit represents an increasing power of 10. This is the number of ones we have, the number of tens, the number of hundreds, the number of thousands, and so on. Now this is probably something you already know, but it's very important to keep it in mind when we talk about binary. Now binary works the exact same way as base 10 positional, but instead of each digit going from 0 to 9, it goes from 0 to 1. Counting upwards in binary sounds like this: 0, 1, 10, 11, 100, 101, 110, 111, and 1000. Because each digit of binary has only 2 values and not 10, each additional digit represents an increasing power of 2 rather than an increasing power of 10. So this is the number of 1s we have, the number of 2s, 4s, 8s, 16s, 32s, 64s, 128s, and so on. Not nearly as efficient as base 10, but exponentially more efficient than tally marks. Literally. So now that we know how binary works, let's talk about computers. Why did the first computer creators, as wise and intelligent as they are, waste their time with such an ineffective system of counting? Well, it's because of a physical limitation on how computers work. Everything a computer does comes down to what's known as microtransistors. Simple, tiny, eensy-beensy little switches that can either be on or off and can be flipped on or off with a very weak electrical charge. The first goal was to get computers to count. And to get them to count by using these switches, we could use the tally system, meaning the number of on switches equals the number of things we have, or we could use the much more efficient system of binary, where each switch represents a digit of binary. 8 transistors using the tally system could represent a number as large as 8 by turning all of them on. With binary, we can represent a number as high as 255. An on switch means a 1, and an off switch means a 0. Now is a good time to mention that a single transistor is what's known as a bit, which stands for binary digit. A byte is 8 of these bits in a row, which means any number between 0 and 255. So if binary is just a system of counting, what do people mean when they explain how to spell things in binary? Well, what they really mean is how to spell things with ASCII. The American Standard Code for Information Interchange is a way to convert a computer's data, which can only be in numbers, and turn it into letters for humans to have an easier time to work with. ASCII simply assigns a character to each value represented by a byte of binary. And because a byte has 8 digits of binary to work with, and 8 digits of binary can represent up to 255 values, ASCII had 255 letters and symbols to choose from, more than enough for the entire alphabet, punctuation marks, and other symbols. For example, the corresponding ASCII number for an uppercase A is 65. Now 65 in base 10 is equal to 1,000,001 in binary. So whenever you type in an uppercase A in a word program, a coding program, or a scripting program or whatever, somewhere there's a little tiny row of 8 transistors arranged in the pattern of off, on, off, 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 on, which represents 0, 1, 0, 0, 0, 0, 0, 1 in binary, which is interpreted as 65 in base 10, which is converted by ASCII into an uppercase A. You're likely starting to get a feel for the staggering amount of transistors required to write something as simple as a Facebook status, let alone all the different coding that your computer has to do to make the screen light up, play games, calculate massive values, and so on. Well, long before we got to the point where your phone can play 3-dimensional games, it became clear that numbers as high as 255 just weren't going to cut it. Regardless of how many bytes we had, and it was a lot, even adding 4 fully active bytes together could only get a number as high as 1020. To solve this problem, new computers were designed to recognize 2 bytes as one single number. So now instead of referencing one line of 8 transistors, computers could reference 2 lines, giving 16 digits worth of binary. This was a huge help because it increased the amount of representable numbers exponentially from 255 up to 65,535. When you hear people talking about the difference between 8-bit and 16-bit, this is more or less it. Now, that doesn't mean that a 16-bit system is exponentially that much more powerful, because your program isn't always going to be utilizing all of these numbers in each byte that it represents. It just has the option to, which opens up lots of doors. Well, this could go on for ages and ages, but I want to end this particular video right here so as not to be overwhelming. In future videos, I will explain how computers use these numbers to decide which pixel is what color on your monitor, what the different components of your computer are for, and how hard drives store binary digits on a spinning disk rather than in transistors. Thank you for watching, and if you enjoyed this video, liking and subscribing.
All right, so that was a little bit of kind of history on where all that binary comes from and how it's used in our technology, not just computers, obviously, but cell phones and anything else that's electronic. So again, just a bit of a recap, being able to kind of understand where all of these things come from is, again, looking at sort of the placeholders and the values. So if we fill stuff out, right, we can get each of the values that we're trying to get. In this case, this first one, we're trying to get 1. So you just put a 1 in the ones place, done. 31, we would put a 3 in the tens place to count for the 30, and then a 1 in the ones place to count for that last bit. 476, 4 in the hundreds, 7 in the tens, and 6 in the ones, and so on and so forth. If we look at the binary, again, it works in a very similar way. If we want something like 1, what we need to do is put the 1 in the ones place, just like normal. Something like 11, though, we wouldn't just be able to put a 1 in the tens place because there is no tens place. So we don't need anything in the 16s. We're not over 16, but we are over 8. So we do need a 1 in the 8s. And then what we can normally do is just subtract off 8 and see how much is left. 11 minus 8 is 3. So we don't have anything in the 4s because 3 is smaller than 4. But we do have something in the 2s. 3 minus 2 is 1, so we still have 1 left over, and we place that last 1 in the ones. So we would have 0, 1, 0, 1, 1. 21 would operate in a very similar way. Again, if we're looking at it, we think, okay, is there anything? Yep, we're over 16. We need to use that. How much is left? Oh, 5. Okay. 8? No. 4? Yes. Put a 1 there, subtract it off. Oh, we've got 1 left. Put it in the ones. We could even code something like 31, which is 16 plus 8 plus 4 plus 2 plus 1 gets us 31. We couldn't put 41. We couldn't even put 32 because we need another column in order to fit those numbers, right? We would need a 32 column in order to fit the next set of numbers. Again, if we were given a binary, we would be able to convert it and figure out what that value is based on the fact that there's a 1 in the 16s place. So 1 there means 16 plus nothing from the 8, nothing from the 4, and it looks like a 1 in the 2 spot. So we have 16 plus 2. We add that up and we would get our 18. So very similar way that we do it with the decimal. We just are a little bit more used to practicing it with our decimal system. Again, trying to write a number, 26 in this case, right? Is it more than 16? Yes. Put that in. Subtract the 16, see what's left, and go on from there. All right. Now, obviously doing this all by hand would be very tedious, and we don't want to do that. So we have computers, we have technology, we can do this automatically. We can code this so that the computer will convert letters into binary for us. We just need to show it how to do that. So again, we're going to look at what are the steps that we need in order to get this thing working and what tools we can use to help. So the key steps that we're looking at, we want to be able to input a 3-letter word. Again, we're trying to keep the signal somewhat short. We don't want to be having you guys out there for hours and hours and hours sending a signal, right? So we want to keep it short. So all we're going to give you are 3-letter words. But we need the computer to split the 3-letter word into 3 separate letters so that we have a way to encode and decode each letter separately. Again, our encoder, we're going to program it to work on a single letter at a time. I would challenge you, once you've learned how to do 1 letter at a time, I would challenge you to think about how you could get it to do multiple letters. Even if it's not at the same time, do a letter here and a letter there and a letter there and be able to put that together or make it look like it's put together. User enters the chosen single letter for encoder to encode. Computer is going to turn that single letter into an ASCII number. Computer is going to then turn that ASCII number into a binary number. Convert the binary into its decimal equivalent. Convert the binary digit into an AM equivalent wave and an FM equivalent wave. And again, we'll kind of show you how we can do that stuff. So this storyboard is again helping us with our telecommunication of like, what are the steps that we're going to need to do? What are the functions that we're going to use? We can think about what functions are going to come up in that process. And we've got a list down here that we'll talk more about later on, but some of the new functions that we'll be using when encoding stuff. Always useful to think about what are the inputs versus outputs whenever we're doing any of this coding stuff. Trying to think about like, is it something that we're going to put in? Is it something that we're expecting the computer to spit out for us? Always useful to kind of think about what's going on with that. So obviously when there's a word like user inputs, well, that's going to be an input, right? But also we are looking at the single letter, right? When we are choosing what letter to encode at a time. And then we're going to have lots of different outputs, and we'll kind of see where some of the functions are that fit in with those outputs. So here, our inputs are highlighted in green. Again, remember that challenge opportunity that I was talking about. See if you could get it to do more than 1 letter, right? You don't want to have to just do 1 letter, send the code, send the signal to somebody else. Do the next letter, send the signal to somebody else. It'd be nice if you saw all 3 of those at the same time, and you could just send the signal, send the signal, send the signal. Some of the functions, again, are going to help us kind of understand what is going on. This mid here part, it's going to be able to cut something into segments, into parts. So that's going to be able to chunk out our 3-letter word into 3 separate letters, right? We'll see kind of how to deal with that a little bit more. This code, again, it's just a built-in function that will do exactly what we want it to do. It'll turn a letter into a number, into an ASCII number. Decimal to binary, again, wanting to be able to convert these things from that ASCII number into a binary string of ones and zeros. It'll always be 8 bits, right? Even if there's zeros leading zeros out in front, it'll always show all of those, so that's important. Again, just kind of knowing what's going on is useful. An if-then statement will help us with 7 and 8, allowing us to like decide what type of picture we want to show. And I know some of you guys had some experience with this when we were doing the car lab eons ago. So yeah, we'll kind of talk about and see how that fits in. And then of course a list of our functions. It's pretty helpful to kind of list off what the functions are and what they are useful for, so that when we're doing our coding, right, we can always look back at that quickly and see, oh yeah, that's what that was supposed to be used for and whatnot. So now we're going to get into the actual coding and get into kind of what is going on there. So if we switch over, right, to this encoder, we can see some of the pictures that we're already looking at, right? That's what a 0 will look like. And we chose this instead of the flat line just to make it a little bit more obvious that we are looking at amplitude changes and not just on or off changes. So that's going to be important. There is a video tutorial in the upper left-hand corner so that you guys can follow along with that video tutorial, and he'll walk you through exactly how to get all of the parts coded. Again, this is just a very basic encoder decoder, but lots of people are looking to challenge themselves to make it better, to make it more user-friendly, right? These are the things that you guys are going to be thinking about how to do. There are even options. This is using Scratch. Put this together the other day. So again, nothing too crazy. I'm typing in my 3-letter word here. And what I programmed Scratch to do was convert that into binary. And then those binary are going to turn into different color flashes on the screen. So again, the same sort of stuff that you'd be doing here, right? Getting that binary, and then one step further of also sending a signal. And so we'd be able to send this out, 0, 1, 1, 1, 0, 0, 1, 1. And again, this would be a message that would be able to be sent to somebody across the hall, and they'd be able to see and make the correct sounds at the correct times for the signal to then get around the corner and to the last person. Again, the goal here is just being able to pass along that message. This way I did it so all 3 letters get sent all at the same time. There's no wait, no pause, nothing. Just send it, right? This, when you end up coding it, you'll get your 3-letter message, and you'll do 1 letter at a time into the encoder. And you'll get your binary signal here. And then you'll put in the next letter, and you'll get your binary. And then you'll put in the 3rd letter, and you'll get your binary. So that can take longer, right? Because you're setting up a system that you're going to have to pause after sending a signal. Get the next letter. Pause. So again, challenge yourself. Think about ways that you can do more than one at a time, right? Or think about how you can have multiple copies all kind of running at the same time so you see all the binaries that you want all lined up. Again, challenge yourself. Try and think of ways to make it more efficient, make it easier and better for yourself. All right. I'll leave you there. Have a great day.